Today, let's talk about the different kinds of chips. There are five you keep hearing about: the CPU, the GPU, the TPU, the NPU, and the LPU. Different names, different companies, different jobs. But here's the surprising part. When it comes to AI, they're all doing the same math. What's different is how each one does it. So let's look inside. But before we do, there's one idea worth having. Because once you've got it, all five of these make sense. Everything an AI model does comes down to two jobs. The first is the math, multiplying huge grids of numbers together. And the multiplication itself is simple. There's just billions of it. The second job is moving those numbers around because they don't live on the chip. They sit in memory, and every one of them has to travel to the chip before any math can happen at all. So picture a workshop and a warehouse across town. The math is the work you do in the workshop. The moving is the driving back and forth. And every chip we're about to look at is just a different answer to those two. First, the CPU, the chip in every computer you've ever owned. Open one up and you'll find a handful of workers inside, and each one of those is called a core. A core is just a worker that can take any job you give it and see it through on its own, start to finish. Your laptop probably has about 8 of them. A big server chip might have 64. And that's the whole point. A handful, not thousands. But here is the part nobody mentions. Most of a CPU isn't doing math at all. Most of it is the machinery for working out what to do next. It reads an instruction, does it, then works out what follows, and it's always guessing what's coming, so it never sits idle. That's what lets it run absolutely anything. Example, loading a web page. The CPU reads the page, runs its scripts, fetches the images, lays out the text, dozens of different little jobs, each one depending on the one before it. Perfect CPU work, but ask it to color 2 million pixels at once, and a handful of clever cores becomes a queue. So the CPU hands the heavy math to a chip built for exactly that, the GPU, and the G tells you what it was born for, graphics, drawing the picture on your screen, 2 million pixels, and every single one needs the same simple coloring step, 60 times a second. That's not 100 different jobs. It's one tiny job done millions of times over. Now, remember what a core was? A worker clever enough to take any job. That's expensive, so you only ever get a handful. And a handful of clever workers is exactly the wrong shape for millions of tiny repeats. For that, you want an enormous number of simple ones. So the GPU makes a trade. Its workers can't take any job. Each one only does the step it's told. In return, you get thousands of them instead of 8. And here's the trick that makes thousands work. They don't each get their own instructions. One instruction is shouted at all of them at once, and every worker does that same step on its own scrap of data. No brain each, just hands. Example, one frame of a video game, 2 million pixels, each needing the same lighting math. The GPU's thousands of workers each take 1 pixel. The same instruction lands on all of them, and the whole frame appears in one go 60 times every second. And for 20 years, that's all this chip did. Draw game worlds, one screenful at a time. Then someone noticed something. Multiplying a grid of numbers is the same shape of work as coloring a grid of pixels. The same tiny step, repeated millions of times. So the chip built for graphics turned out to be exactly the chip AI needed. That accident is the entire AI boom. Now, the GPU is fast because it has thousands of workers, but those workers still wait for instructions. Shout, work, shout, work. Google ran the same math billions of times a day and asked, if the job never changes, why keep giving instructions at all? That's the TPU, the T is for tensor, just a big grid of numbers. And the idea couldn't be simpler. The math is built into the chip's shape. No instructions, no deciding. Numbers pour in one side, flow through a grid of tiny calculators, and the finished answer streams out the other side. That's the entire chip. It can only do that one thing, but it never stops and it never waits. And each number is fetched from memory only once. Remember the warehouse? One trip, hundreds of uses. Example, every Google search you've ever made. Each one runs through these grids. The question becomes numbers. The numbers walk across the TPU and the answer comes out the other side. Billions of times a day on the exact same wired in math. That trick was built for data centers, rooms full of chips with all the power they could ever want. But your phone wants AI too, face unlock, cleaning up your photos, hearing you the moment you speak. And a phone has a budget that a data center never worries about, the battery. So that's the NPU's job. The N is for neural, just the kind of math AI models are made of. It's the same specialization idea as the TPU, only rebuilt to save power instead of chasing speed. And it manages that with two moves. First, it does the math roughly. A big chip works in long, precise decimals, and the NPU rounds them off to simple whole numbers. Because for recognizing a face, the rough answer is the answer, right? And it costs a tiny fraction of the power. Second, the model it runs is small enough to sit right beside it, so nothing has to travel far. Example, face unlock. Your phone turns your face into those rough whole numbers, runs them through the small model sitting right on the chip, and matches you in a fraction of a second. That's how it checks your face 100 times a day, and the battery never notices. And then there's the extreme one, the LPU from a company called Groq. The L is for language, and it exists because of one painful fact about chatbots. Every chip so far still keeps its model in the warehouse, in memory, off to the side. And a model writing you an answer writes it one word at a time. For every single word, the whole model gets dragged out of that warehouse again. Every word, another trip. So even a monster chip spends most of its time just waiting. The LPU's answer is blunt. Don't use the warehouse at all. Take the entire model and keep it on the chip itself, in the small, fast memory sitting right next to the math. No trips, because there's nowhere left to drive. Example, ask a chatbot running on Groq a question. The answer doesn't crawl out word by word. It lands in one block, hundreds of words a second, faster than you can start reading. Same model, no trips. Now, here's the part people get wrong. Everyone asks which chip is fastest. But when AI feels slow, when a chatbot is typing back at you, it's usually not the math that's behind. The chip is waiting for numbers to arrive from memory. So the real question was never how fast a chip can think. It's how fast the numbers can reach it. So now you know where the time actually goes. When a model writes you an answer, every word costs a tiny bit of math and one enormous haul out of memory, again and again, word after word. The chip isn't thinking hard, it's waiting. The speed you feel isn't the math, it's the fetching, and that's exactly what the LPU was built to avoid. So, in a nutshell, the CPU, the general one, a few clever cores in every computer, able to run anything. The GPU, thousands of simple workers, born to draw graphics, perfect for AI's repeated math. The TPU, Google specialist, the math wired straight into the chip for one job at massive scale. The NPU, the small one in your phone, rounding the math to spare your battery. And the LPU, the chat specialist, the whole model kept on the chip so answers come back fast. Never competitors, different jobs, the same math, 5 ways of doing it. That's it for today's video of KernelCast. Stay tuned for more.